Hello friends, welcome back to my YouTube channel. This is part number 4 of my discussion on adsorption, and from this part I will start discussing adsorption isotherms. And today in this particular video I will be talking about the simplest adsorption isotherm that can be used to represent adsorption equilibrium. So as you know, in my earlier videos, if you have seen my earlier video where I had discussed how to represent adsorption equilibria, and one of the way or the commonest way of representing adsorption equilibria is plotting of adsorption isotherms. And there are different types of adsorption isotherms. I'll shortly tell you about those types. Out of those, first, in this particular video, I will be discussing the simplest adsorption isotherm. So let us start the discussion. Okay, so let us begin the discussion. There are many theories available in the literature that explain the phenomenon of adsorption. But the problem with this theories is there is not a single theory that will explain all the adsorption phenomena. That is the problem. So if you have a theory that can be applied to one situation of adsorption, the case may be you may not be able to apply the same theory to some other situation. So that's why I'm saying not a single theory explains all the adsorption phenomena. Even though you have many theories, but the problem is there is not a single theory that explains all the adsorption phenomena. So with this background, let us move ahead. For engineers, we don't need every minute detail, every minute theoretical detail about adsorption. Engineers do not need every minute theoretical detail. They are more concerned, we engineers are more concerned with how is equilibrium reached during adsorption. This is one thing. And the other thing is how to represent the adsorption equilibrium accurately. So there are two things with which we engineers are concerned. One is how equilibrium is reached during adsorption, and then the second one is how to represent the adsorption equilibrium, and that too accurately. Why this is important for us? This is important because this will be useful for us for designing the adsorption equipment. So if you know how equilibrium is reached during adsorption, and if you are able to represent the adsorption equilibria accurately, then it will be useful for us for designing the adsorption equipment. So for doing this, we have some earlier theories that are quite useful. Most of these earlier theories, most of them have been developed for gases. The reason is the gaseous state is more easy to understand than the liquid state. For gaseous state, we have the kinetic theory of gases that we explain the behavior of gases. So that's why many of the earlier theories that were developed for gases, and you can use this, we engineers can use these theories for carrying out these two tasks, for understanding how the equilibrium is reached, and then for representing the adsorption equilibrium, because that will help us in designing the adsorption equipment. So most of the earlier theories, they were developed for gases, as the gaseous state is more easy to understand than the liquid state. Now some statistical theories are being developed, and what is the significance of this statistical theories? These statistical theories, they can be applied to both gases and liquids. But even though you have this particular situation, all these theories are not at a stage when you can use them for designing adsorption equipment with confidence, with ease and confidence. So even though we have some earlier theories that can be used, you have some statistical theories developed for gases and liquids, but these theories are not at a stage when they can be applied with confidence or with ease to design adsorption equipment. So that is the problem with this theories. So let us move on it. So I have talked about representing equilibrium in my earlier video. This is just a summary of that discussion. So at equilibrium, when you have equilibrium between the fluid phase and adsorbent phase, that is fluid phase and solid phase, three parameters are involved. Which are these three parameters? You have the concentration of the adsorbate in the fluid phase. Let us denote it as Ca. And then you have concentration of the adsorbate on the surface of the adsorbate. And we are going to denote that by Cs. And the third parameter that is important in this case is the temperature, T. Now, when you have these three parameters decides the capacity of the adsorbent to adsorb a particular component. It depends on how these three parameters interact among themselves. The point is the capacity of a adsorbent to adsorb a particular component. It depends on the interaction between the above listed parameters. Concentration of the adsorbate in the fluid phase, then concentration of the adsorbate on the surface of the adsorbent, and then the temperature. Now, in order to represent the equilibrium in a simple way, one can say what you can do in order to represent the equilibrium easily. What you can do, one of the above listed parameters is kept constant, while the other two can be varied. So out of the three parameters, you can keep one constant and then vary the other two. And depending on how you get the adsorption data, you can use that data to represent the adsorption equilibrium. So the point is, to represent the equilibrium, one of the above listed parameters is kept constant, while other two are varied. So accordingly, there are three different ways of representing the equilibrium. There are three different ways of representing the adsorption equilibrium. Adsorption equilibrium. Which are this? First is, you can plot Ca against Cs. That is concentration of the adsorbate in the fluid phase against concentration of the adsorbate on the adsorbent by keeping T constant. Then what else you can do? You can plot Ca against T by keeping Cs constant. Concentration of the adsorbate in the fluid phase, it is plotted against temperature by keeping concentration of the adsorbate on the surface of the adsorbent constant. So this is another way. And the third way is, you can plot Cs against T by keeping Ca constant. So in this way, you can represent the adsorption equilibria in three different ways. And accordingly, you have three different types of adsorption equilibria. Okay, so let me just tell you, you have the adsorbent. I'll just quickly tell you the situation. And let us say that you have a gas mixture. You have a gas mixture. This yellow molecules. This is mixture of A plus B, where A is represented by blue color and molecules of B, they are represented by yellow color. So concentration of A when it is in the fluid phase, we are denoting it as Ca. And then when molecules of A get adsorbed on the surface of the adsorbent, then the concentration on the surface of the adsorbent, we are denoting that by Cs. And then you have the third parameter is temperature. So accordingly, Ca can be plotted against Cs by keeping T constant. Ca can be plotted against T by keeping Cs constant, and Cs can be plotted against T by keeping Ca constant. So in this way, these are the three ways in which you can represent the adsorption equilibrium. I hope you have understood the concept. If you have any doubts, you please mention them in the comment section. Now, since the title for this discussion is adsorption isotherms, so let me just tell you, you must have seen my earlier video. Adsorption isotherms, these are one of the ways of representing adsorption equilibrium. So let us understand more about adsorption isotherm. So how are you going to get adsorption isotherms? You are going to get them by plotting Ca, that is concentration of adsorbate in the fluid phase, against Cs by keeping T constant. So if you look at the nature of the graph that you will be getting, you are plotting Cs on x-axis, Ca on y-axis, then you will be getting a curve, and this curve is nothing but the adsorption isotherm. Why isotherm? Why we are calling it as an isotherm? Because we are keeping temperature constant. So the resulting curve is called the adsorption isotherm. And as I said earlier, this is the commonest way of representing adsorption equilibrium, and that's why we are discussing it in detail. So this is the commonest way of representing the adsorption equilibrium. Different adsorbates will give different adsorption isotherms on the same adsorbent. I have talked about it in my earlier video. I am giving link to the entire playlist of my videos on adsorption. So one is different adsorbates will give different adsorption isotherms on the same adsorbent, and the other thing is the same adsorbate will give different adsorption isotherms on different adsorbents. So now our task is to know more about this adsorption isotherms, and today we are going to understand the simplest adsorption isotherm. So let us move ahead. The simplest adsorption isotherm. Before we talk about simplest adsorption isotherm, I will tell you about all the adsorption isotherms that are being used. So first you have the simplest adsorption isotherm, which I will be discussing today, and this is applicable to those cases where the adsorption mechanism is very simple. So if the adsorption mechanism is very simple, you can represent the adsorption equilibria by using the simplest adsorption isotherm. So the simplest adsorption isotherm, it is applicable to those cases where the adsorption mechanism is very simple. But the problem is very few systems are simple. That means there are very few systems, or there are very few applications for the simplest adsorption isotherm. What is the reason for that? The reason is this simplest adsorption isotherm is applicable to those adsorption mechanisms which are very simple. So the simplest adsorption isotherm, it is applicable to those cases where adsorption mechanism is very simple. But the fact is very few systems are simple. The commonly used adsorption isotherms, if you cannot use the simplest adsorption isotherm, what other options do you have? Let us understand. The commonly used adsorption isotherms, one is the Langmuir adsorption isotherm. Then you have the Bronner, Emmett, Teller, that is BET adsorption isotherm. Then you have Gibbs adsorption isotherm. So I will be discussing all of this. Today I am discussing the simplest adsorption isotherm. The commonly used adsorption isotherms are Langmuir adsorption isotherm, then Brunner Emmett Taylor, that is BET adsorption isotherm, and the Gibbs adsorption isotherm. These three adsorption isotherms, these are based on various theories for gases. But none of these isotherms are applicable universally. You cannot apply this to all the situations. Not a single adsorption isotherm out of these three can be applied to all the situations. So that's why I'm saying none of these isotherms, they are applicable universally. And the other important thing that you have to notice, these adsorption isotherms, the Langmuir adsorption isotherm, Brunner Emmett Taylor, that is BET adsorption isotherm, and Gibbs adsorption isotherms, they are applicable to adsorption of gases. Very important information. These three adsorption isotherms, they are applicable to adsorption of gases. And there is one more adsorption isotherm, the Freundlich adsorption isotherm. This is not based on any adsorption theory. While the previous three, they are based on various theories. The fourth one, Freundlich adsorption isotherm, it is not based on any adsorption theory. This isotherm is applicable to adsorption of liquids. So you have one adsorption isotherm which is not based on any adsorption theory and which is applicable to adsorption of liquids. Further, this is applicable over a small concentration range. Again, you can call this as a limitation. You can apply Freundlich adsorption isotherm to adsorption of liquids over a small concentration range. I hope you are understanding it. The other thing is the Freundlich adsorption isotherm is applicable for dilute solutions. It is applicable over small concentration ranges. The second is it is applicable for dilute solutions. So at the end of this particular discussion, now we know we have the simplest adsorption isotherm, which I am going to discuss, but it is applicable to simple situations which are very rare. Then you have some commonly used adsorption isotherms, the Langmuir adsorption isotherm, Brunner Emmett Taylor, that is BET adsorption isotherm, the Gibbs adsorption isotherm. These are based on theories, but none of them is applicable universally, and these are applicable to adsorption of gases. Then you have the fourth adsorption isotherm, the Freundlich adsorption isotherm, which is not based on any adsorption theory. It is applicable to adsorption of liquids, it is applicable over a small concentration range, and it is applicable to dilute solutions. Now we know in my coming videos, I will be discussing all this. Today, I will talk about the simplest adsorption isotherm. Let us move ahead. Okay, so let us talk about the simplest adsorption isotherm. So many earlier theories that were developed for describing the phenomenon of adsorption, they were concerned with adsorption of gases. The reason for this is the behavior of ideal gases. It is easily predictable. Why so? Because you have kinetic theory of gases for them. So kinetic theory of gases, it can be used to predict the behavior of ideal gases. This is one thing. So you can have simple adsorption mechanisms that you can postulate to tell how adsorption occurs, adsorption of gases occurs, because you know the theory, you have the theory, kinetic theory of gases, and with the help of this theory, you can predict the behavior, and therefore you can postulate how adsorption may happen, how adsorption may take place. So with the help of kinetic theory of gases, you can postulate simple adsorption mechanisms. This is one thing. Then you can get equations that relate Ca and Cs. So I hope you know Ca is concentration of the adsorbate in the fluid phase, and Cs is concentration of the adsorbate on the surface. So equations relating Ca and Cs, they can be proposed with the help of this kinetic theory of gases. So you can postulate the mechanism, and then you can derive equations that will describe the mechanism. So this is possible for ideal gases, or you can say this is possible for gases. You can assume them to behave ideally, and if they are behaving ideally, you can use the kinetic theory of gases. So simple adsorption mechanisms, they could be postulated. Equations relating Cs and Cs, Ca and Cs, concentration in the fluid phase and concentration on the adsorbent surface, relation between these two concentrations, they can be easily predicted. So as at very low concentrations, when you have a mixture with very low concentration of the component that is to be adsorbed, then what you can do, at very low concentration, the adsorbed molecules are widely spaced on the surface of that on the adsorbent surface. At very low concentrations, the adsorbed molecules are widely spaced on the adsorbent surface. I will show you the mechanism. So in this case, when you have widely spaced adsorbent molecules on the surface of the adsorbent, in this case, in such a case, one molecule has no influence on the other molecule. One molecule has no influence on another molecule. That means molecules, when they are on the surface of the adsorbent, they are not going to interact among themselves. I will tell you. I will shortly show you the schematic. So let us say that you have this adsorbent, and this is contacted with a gaseous mixture of gas A and gas B. Now, according to this particular theory, the simplest mechanism, what happens? The adsorbent molecules, they are getting adsorbed on the surface of the adsorbent, but when they get adsorbed, they are widely spaced on the surface of the adsorbent, and they are not affecting each other. So for example, you have this molecule of gas A, it is not going to affect this molecule, this is not going to affect this molecule, or this is not going to affect this molecule. So they are widely spaced on the surface of the adsorbent. This is one thing, and they do not interact among themselves. So the mechanisms, this simple mechanism postulates this particular behavior. When the adsorbent molecules, they get adsorbed on the surface of the adsorbent, they are spaced widely, they are separated by appreciable distances, and they are not interacting among themselves. So this is the simplest mechanism that can be postulated for adsorption of gases, and then you can assume those gases to be behaving ideally. So are you understanding it? So this can happen at very low concentrations. So at very low concentrations, the adsorbed molecules are widely spaced on the adsorbent surface, and therefore one molecule has no influence on the another molecule. That is, the adsorbed molecules will not interact among themselves. This is the simplest mechanism. Now let us mind. This is the simplest mechanism, as I said. Okay, so for this simplest mechanism, where you have adsorbed molecules on the surface of the adsorbent, widely spaced from each other and not interacting among themselves. So when A is in the fluid phase, that is when A is in the gas mixture, its concentration is Ca, and when it is on the surface of the adsorbent, its concentration is Cs. For gases, the best way of expressing this is partial pressure of A. We will talk about it later. So for time being, Ca is concentration of A in the fluid phase and C is concentration of A on the surface of the adsorbent. So at equilibrium, that means when equilibrium is reached, which would be the dynamic equilibrium. I have talked about it in my earlier video. Link is available in the description section. So at equilibrium, Cs is directly proportional to Ca. That is concentration of the adsorbent on the surface of the adsorbent. It is directly proportional to concentration of A, concentration of the adsorbent in the fluid phase. So mathematically, you can express this as Cs is directly proportional to Ca. And then you can introduce a constant of proportionality. So it will be Cs is equal to Ka into Ca. I am calling it as equation 1. In this case, Ka is the proportionality constant, and equation 1 is analogous to Henry's law for gas liquid system, where you are relating concentration in gas phase to concentration in liquid phase, the Henry's law. So equation 1, which predicts the simplest mechanism of adsorption, it is analogous to Henry's law for gas liquid systems. And the proportionality constant Ke in this particular case, it obeys Van 't Hoff equation. What is that equation? The equation is d of ln of Ka by dt is equal to d delta H upon RT square. The proportionality constant also obeys Arrhenius equation. What is that? Ka is equal to K naught e raised to minus delta H by RT. So for the simplest case, the proportionality constant obeys Van 't Hoff equation. It obeys Arrhenius equation. So in this case, delta H is the heat of adsorption. Delta H is the heat of adsorption. So the simplest adsorption isotherm is given by equation 1, where concentration on the adsorbent is directly proportional to concentration in the fluid phase. So that is the simplest adsorption isotherm. So the simplest adsorption isotherm is Cs is equal to Ka into Ca. So that is Ca is equal to 1 upon Ka into Cs. I have rearranged it. Ca will be equal to 1 upon Ka into Cs. So what can you say about this equation? This equation is of the form y is equal to mx. This equation is of the form y is equal to mx. In this case, y is Ca and x is Cs, and m is the slope. And in this case, slope is 1 upon K. So that means if you plot Ca on the y-axis, Cs on the x-axis, you'll be getting a straight line. The simplest adsorption isotherm would be a straight line that passes through the origin. The slope of this straight line is 1 upon Ka. So in this way, you can represent the simplest adsorption isotherm. The simplest mechanism predicts that concentration on the adsorbent surface is directly proportional to concentration in the fluid phase. And the adsorption isotherm, it can be plotted in this way. It is a straight line that passes through the origin. So that is all that I want to discuss for the simplest adsorption isotherm. I hope you have understood what is the simplest mechanism for adsorption of gases on the surface of adsorbent and what is the simplest adsorption isotherm. If you have any doubts, please mention them in the comment section. With this, I will end my discussion for this particular video. So at the end of this discussion, I am sure you must have understood the simplest adsorption isotherm. So with this, other thing is, even though this is very simple, unfortunately, very few systems are so simple like this. There are very few systems to which you can apply the simplest adsorption isotherm. You'll have to go for the other commonly used adsorption isotherms, which I'll be discussing in my coming videos. For this video, I will stop my discussion. Thank you for being with me. In my coming videos, I'll be discussing the other adsorption isotherms. So, thanks for watching this particular video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. And I'm sure you'll be with me in my next video where I will be discussing the lamellar adsorption isotherm. For now, have a nice day. Bye bye.